But good job. All right, so I'm Matt Sylvester. I'm going to cover the water storage portion of this. So this is session 5. This will cover, kind of do a little overlap of the water main installation slash like distribution portion that I discussed yesterday. So here we go. So as I said, this was the first slide of the distribution or the water main installation session that we had yesterday. Basically, as we are aware, as we discussed, the distribution system is there to basically bring water from a source, from a treatment plant to the customers, to the residents, whether that's treating it at the treatment plant and then delivering that out. And it's obviously a large asset. And one of the biggest points on this slide that I want to drive home is that question there at the end is like, what is the most important thing maintaining water potability? Okay. And if you remember from yesterday, that was maintaining pressure. Okay. So that's why we're getting into, water storage today, because that's the, probably single most thing that is going to be focused on over chlorine residual and everything else. Maintaining pressure is definitely important. So again, same slide. Basically, we're going into major system components. So we have the source, obviously. You're having your treatment plant itself, but then from that, you're talking, your transmission mains. That's delivering that large volume of water, to the extents of the system. And then having your distribution mains that are slightly smaller, kind of delivering that directly to the customers themselves. Okay. From that, again, we got to maintain that, storage. So you're treating this water, you're storing that water up, whether that's with pressure, without pressure. So we have different types of storage, available. So that's gravity, if that's ground, if that's hydropneumatic, that's what that HP is standing for there. You have valves and hydrants, you have booster pumps. And then you have service leads that actually is that individual home delivery. Okay. So why do we need storage tanks? Well, I would say that, for the most part, these are all pretty relevant. I wouldn't say that this is any sort of like hierarchy of what's, most important or not. Obviously, as we just discussed, maintaining that pressure is a huge aspect of this. But fire storage is a big one. Obviously that, keeps your, insurance in good shape. You're always available, or water is always available if a fire to break out. Okay. And again, maintaining that pressure for that portion there. Smoothing out your peak demands, whether that's the morning or the evening, peaks. So you're not having the pumps just doing all the work there. You have that storage on hand. Maybe your capacity isn't, your well capacity itself or treatment plant capacity itself isn't able to keep up with those peak demands, but with enough storage, you might be able to overcome that, or ideally it would be designed to overcome those things. Okay. Again, maintaining system pressure. That's going to be, the main focus of this whole presentation. Obviously there's the reliability aspects. If for whatever reason, a well goes down or a treatment plant portion, goes down, you at least have some buffer there, some clean water that's stored, and being able to deliver it to the system. You also have pump cushion. Okay, so when the pumps kick on, there's not this excessive surge in pressure throughout the system that might, disrupt the water mains or disrupt service lines, things like that might cause rupturing and breaking of the lines. Okay, so gives a little bit of buffer there when those pumps or just pressure in general spikes. Okay. Kind of in that same idea of smoothing out those peak demands, you're also allowing off-peak pumping. So instead of pumping, especially if you're purchasing from somebody, there's high time, times that pumping or getting water delivered to you is going to be more expensive. So if you can do that on those off times, that's going to be more cost beneficial to you. Okay, so you can do that at night, fill the tower overnight, and then continue on from there. Okay. And then obviously there's, the smaller portion of that, but it's still important, is the community identity. People love to paint their towers or have their logos or things like that, that really stand out and give your community some sense of pride, right? It's at one of the few things that you really see in the distribution system in any given community for the drinking water side of it. Okay, everything else is buried underground and nobody cares, but they might care about the water storage. Okay. So as we discussed yesterday, these are kind of your common system layouts. You have a grid pattern, you have a branching pattern, maintaining that circulation of flow. As we discussed, this is usually kind of a combination. Most systems are a combination of these, where you usually have some looping going on, but then you also have some dead ends. Now, that one additional point here, as we're discussing the storage tank portion of this, is those are laid out. So depending on which way your system is designed, maybe that storage tank is located, farther away or closer to treatment plant or well houses or things like that. Okay. So some things to consider for your storage tank, both currently and going forward in the future. Things that you got to keep in the back of your mind. Okay. So just in general, locational aspects of where you're going to put your storage tank is going to be closer to the source. Is it going to be closer to the customers? And I'm going to actually tie this into that second to last bullet point, that topography portion of that. Maybe you're in a hilly location. Okay, so maybe it's more beneficial to put that tank, up on top of that hill, so you constantly have that pressure going on. Yes, you'll have to probably pump up to it depending on the situation, but at least you have that reliability that you're always going to have pressure as long as that tower is filled. Okay, or that storage tank in general is filled. Okay, number of customers, and this kind of plays into that second bullet point, right? Anticipated demands. So how many customers do you have? What's the expected amount of water usage from those customers? Is it based on average day? Or, are you basing your design of your tank based on average day, max day, peak hour, those types of things you can consider? Okay, and obviously the number of customers can greatly affect that. You can also maybe focus on, maybe you don't have a lot of customers, but you have a lot of industry, and maybe that industry uses a lot of water. So it's kind of this balance here. You got to figure out what fits best for your individual system. What's your usual, demand of water, okay? And then also design for fire flow. Again, maybe industry demands, or wants you to have larger capacity, larger storage, because they have, maybe a potentially flammable product that they're producing. Okay, so it's trying to maybe meet their meetings, meet their goals, whatever that situation might be, rather than just, okay, we have a hydrant because this is a residential area or something like that. Okay, so you might need more flow, might need more fire flow if you have large industrial complexes, things like that. And then that last one, I think it's adequate that's put at the end, is cost. Again, there's lots of other things, important things that probably come before cost. Yes, cost is important. That's why it's on the list. But there are other things that can be, it's much more important to be delivering a high quality of water with a acceptable amount of pressure, maintaining safe fire flows and things like that, over maybe some costs. But costs do play into it. So is that capital cost? Isn't that upfront cost to put a storage tank in or to get a new one, versus what's your yearly, your monthly, whatever that is, your maintenance look like? How much is that going to cost when you got to paint that tower again? How much is that going to cost when you have to put a new internal epoxy liner or something like that? Okay, again, all things to consider. So as you're going through that design process, this is just drawing your attention to, there are recommendations, there are guidance, there are rules that you need to follow. So you got Act 399, that's a big one. You got 10 state standards, that's also another big one. And then you have suggested practices. All have, their own, portions. They might overlap to some extent, but each gives a little bit more, information and guidance as you go through them. Okay, so make sure you're meeting those as well, or at least to the best of your ability. So storage tanks and design considerations. So what's your normal hydraulics of the water system? Again, is it high pressure districts? Is it low pressure districts? Is there, abnormal topography? Is it, is there large demand from an, industrial, area, or is it mostly residential? All these things kind of can go into what's making up your system. Maybe you have a small system, so you don't need a whole elevated, storage tank or something. So maybe that just feeds into, maybe you just need some pressure tanks, versus maybe you need something more. Maybe you need a lot of volume. So you put a ground storage tank, but do you want that to be gravity fed, or do you want that to be with high service pumps? Okay, so things to consider. And then, you have if you're going with the pressure tank route, are you going hydropneumatic? Or are you going to go with a, bladder tank? Okay, again, kind of that option of, are you going to pay, that maintenance fee every so often? Or are you going to do a full, replacement of them? What's easiest, what's most beneficial? Again, lots of things that go into it. So engineering considerations, again, kind of driving that point home on how you determine what you should be using, what you should be selecting and engineering as you go through it. So is there elevation differences? Different pressure zones. Again, do you need one tank? Do you need multiple tanks? If you put that elevated storage tank, too high up, is that going to be too much pressure for one of the, extents of the system that's lower or something? Maybe it's really good for one portion of the system, but it's not good for another. Okay, so maybe you're putting in a pressure relief valve that Scott just talked about. Again, you got to keep all aspects in mind. Okay. So is a large area? Is it remote areas? Is there future growth? Is it a young population that's all getting married and having kids, or is it an older population that's starting to dwindle? Playing into that cost again. Is it initial upfront capital costs, or how much are you going to put into building a very large storage tank or reservoir? Versus how much is it going to cost to make sure that you're maintaining that as well, painting and cleaning it out and draining it and things like that on a whatever frequency, 5 years, 10 years, 15 years. Okay. So and then making that decision, right? So you can have multiple options, but what are you looking to do at the end of the day? Are you providing storage? I would say for most systems, they need some form of storage, but is it a large amount? Is it a small amount? Can they get away with hydropneumatics? It's all probably dependent on what your system, capacity is. Okay. So if you are putting in storage or, large storage, is it going to be ground? Is it going to be gravity? Is it going to be hydropneumatic? Again, you have lots of different options, even between those three general concepts of what a storage tank is. So this is just a, probably, straightforward diagram here. So this is just kind of a direct pumping system. There's no storage here. It's just taking it from the source, taking it to that treatment plant, and then delivering that to the distribution system. Okay. According to speaker notes here, which I was not aware of, apparently the city of Detroit is an example of this. They are considered a direct pumping system. Okay. This is a combination system. As you can see, we now added a little storage tank here. So it's still the same thing. You're getting water from the source, you're treating it here, and then you're putting into this elevated storage tank that's maintaining pressure to the rest of the distribution system. This is a gravity system. Okay, so this is actually, this dam build up here. You're having, that pressure building up here. So it flows into the plant, flows to the distribution system. Okay, lots of different examples of this. So this is a hydropneumatic tank. This is commonly referred to as an iron lung. This is not a bladder tank. Okay, so just straight hydropneumatic, meaning basically that's meaning that is a steel tank here on the left, that there is some portion of this that is air, compressed air, and then you have water down below. So it holds probably a large volume of water here, but that pressure is maintained with good water or with good air pressure. Okay, this is different than these here. These individual ones, we would call these bladder tanks. Also hydropneumatic, they're running off of air, pressure, and water. Okay, but there's an actual bladder in here that's keeping that water, separate from the air itself. All right. Now, with that previous one, This can be, maintained. This can be taken out of service and cleaned and painted and everything else. These cannot be. Okay, once that bladder fails, that's pretty much, that's not a repairable portion of that. Those will need to be replaced. Okay. So again, you're still maintaining these. There's little air check or air valve up here that you can charge these and make sure that that pressure is proper and at an adequate rate. So you're still having that combination of good storage of water as well as that pressure for whatever you're trying to meet in that system. Okay, this is another example of an iron lung hydropneumatic tank. Now, this is kind of a unique one because this is what we'd call partially buried. Ooh. Partially buried. So as you can see here, this is the wall, probably have a well house right here. Again, there's a little manhole there. So if you were to ever take it out of service, you can clean the inside of it or do painting, I guess, theoretically, if you need to. This is a sight tube here. This kind of tells you where that water level is at. You can see like they probably marked it with a, Sharpie, maybe some tape or something to kind of have an idea of where they're at. Maybe this is normal operating pressure. There's their max pressure here. And then this their lowest. So in between that point, they're in good shape. Okay, but then they have a decent idea of what that air pressure is as they're going along. Looks like over here, it's maybe a little hard to tell, but I would say that looks like a air compressor of some kind. And that's, basically making sure that this is properly pressured. You can see the gauge up here, feeding that air if need be. All right, so water comes in and out of this point with, a certain amount of pressure. All right. Again, here's some bladder tanks. These are slightly larger than the ones that we just saw, but so they have a little bit more capacity, but same kind of thing. They have bladder here somewhere, or well, I guess it's a little different, but but the air pressure is maintaining that. Okay, so you got to make sure that they're properly charged, just like you would with that hydropneumatic tank. But once the bladder fails, they're pretty much out of commission. Okay, so this is just a conceptual kind of concept of this. Again, you have this air, you have the green portion here, that is the bladder. You have the blue here, light blue, that's the water portion of that. So this would be a bladder tank, and versus that iron lung portion of this. We typically just call this hydropneumatic, even though they're probably both technically a hydropneumatic tank because they're working off of that air pressure. Okay. So gravity tanks. So this is well house or treatment plant over here. This is your gravity tank here. As you can see, there's some vents here, to relieve that air pressure, because these are not under pressure, or at least ideally they shouldn't be under pressure. Not sure exactly the layout of this, but there's a potential that this is actually 4 separate chambers, just because there's 4 different valves or 4 different vents here. Okay. So here's another example of just a ground storage tank. Again, according to the speaker notes, I'm not aware of this specific instance, but this is actually considered somewhat of an elevated tank. So this is up, uphill. So you have your well house here. This is uphill of whatever the community is. So that's actually maintaining pressure to the system because it's on a higher elevation, basically. But same kind of thing as you would any, most of your large storage tanks. You have an overflow here. You have an actual inlet outlet here. If you're to ever do rehab on that, and then you have a vent way up here. Okay, so this is actually maintaining pressure in this given situation. Okay, so this is actually 2 combinations here. So you have your elevated storage tank up here. This is a 50,000 gallon versus your 750,000 gallon right here. You can kind of see it, it's all covered in snow, obviously, but this is kind of doing, kind of the best of both worlds here. So it's kind of maintaining that pressure if need be, but then you also have, large volume there if you ever, need to meet those peak demands, or maybe you have a fire situation, things like that, that kind of run off this ground storage is actually run off of booster pumps. Okay, so it's actually feeding that to the system. Okay, this is a 500,000 gallon storage tank. This is actually a building on the outside, so not the tank itself. This is just north, this is the location just north of Houghton. Basically, the main point here is that this is it was originally built in 1895. So this is still standing, still operational, still functioning. So that's what, 127 years old at this point, and it's still running. So obviously this is the exterior portion. They kind of basically built a building around it, to maintain that tank, this large standpipe, we would typically call it. Okay, so that's your little landmark there, and this is the interior portion of that. So you have your steel on the right here, and then that's that exterior portion of the building. Okay, so it's still in good shape, put together, still providing water to that community. Here's another example of a storage tank. This looks like, I'm guessing that's Houghton Hancock area right there. You got two vents here. So this is a dual compartment. So it's split somewhere down the middle here. You got two hatches that you could gain access to the top of that, and holds large volumes of water. Okay, so here's your elevated storage tanks, or some examples of them. Obviously, there's lots of different designs, heights and just shapes in general that can hold different volumes and different pressures and things like that. Okay, so this one here for foresight, this is what we call a pedestal tank. These two at the top and the left and right here are what we call multi-leg tanks. This right here is what we call a wet riser. So it's a large diameter wet riser. It's very large, piping that runs up. But this is actually not an insulated portion here. But because so much volume of water is moving, that there's not typically, concerns for freezing. Okay, this on the other side was, somewhat of a, more narrow pipe that runs up here, and they were having issues with freezing. So this was originally a wet riser and was later converted to an insulated dry riser. So this, this exterior portion, what you can see right here, there's actually a pipe that runs up the middle of it. Okay, that's now insulated from the direct weather conditions, so they're not having those same issues with freezing and whatnot. Okay, this is just Disney here. So obviously you can get them very customizable. Again, kind of talking about that community brand name, if you will. So kind of unique there. This is a pretty standard tank. This is probably what you see most often. Again, pedestal tank, standing, above, holding the volume up here, holding the majority of the volume of water up here. So it maintains that pressure throughout the distribution system. I kind of alluded to standpipes earlier. So standpipes are basically a large cylinder that just, increase however tall, however wide, whatever diameter they are. But they're basically just, a large, coffee can, if you will, that holds water versus your elevated storage tank that we just discussed. So it's holding that, not, the majority of the volume of water is not sitting here, but sitting at that higher elevation. Standpipe might typically hold more volume, but that can come with, some not great portions of that as well. So you can start getting aesthetic water quality complaints. You might not have the same kind of pressure maintained, especially as you drop. So now you're just kind of fluctuating in a shorter zone where you could theoretically use this full tank and still maintain, decent pressure in the system. But the standpipe, you can only use a couple of feet before you're going to have to fill it back up to get adequate pressure again. But again, there's all this water that's still sitting here. So maybe that's, getting rid of maybe chlorine residuals if it's sitting for a long time. Maybe that's developing disinfectant byproducts, things like that. That can be, again, harmful and aesthetically, not pleasing. Okay, so that can be a challenge for sure. So as you just seen, that was just a little animation there. So, it's still got to operate kind of in that higher zone there. Okay. Operational issues dealing with stagnation. So there's lots of ways to overcome this or try to overcome this. Some of it goes into the direct design of a storage tank, and then some of it goes into add-on portions, right? So whether that's diffusers, whether that's mixers, these are a couple of examples of that. Trying to stir that up, trying to move that water around, so it's not just maybe you're just short circuiting it. So you're just having water go from the inlet to directly to the outlet. It's just getting this portion, but it's not touching this whole second half of the tank maybe. So getting diffusers in there, getting mixers in there, maybe that's stirring that up, getting that turbulent flow, into the tank. That's getting it mixed together and then getting a more consistent output. Okay. There we go. Oh, you can also fluctuate by doing this. You can also fluctuate the heights of the elevated storage tank. That's what that animation there was just showing, to get, again, maybe some better mixing, better usage of water. So you're not having this stagnant water sitting there for a long period of time and degrading and forming, DBPs, things like that. Okay, this is just an example, of a plan sheet here. You have an elevated storage tank that's being designed. You have this elevated kind of, inlet nozzle here. So it's going to be spraying out of these 3 different portions here at a higher elevation, or at a higher point in the storage tank. Okay, but and this is not always the normal. Sometimes it's just an inlet and an outlet, just a single point coming in and out. This point here, if you can see, is the outlet. So you're getting water coming up and out, spraying in multiple directions, and then you're having water leave the tank out a different pipe. Okay, so coming out at the top and then leaving out the bottom. Okay, so it's probably going to get some pretty adequate mixing because of that. Okay, and though maybe it's not the norm, maybe it costs a little bit more, it might be beneficial, especially if you're dealing with long periods of stagnation for that water, which are leading to DBPs and other things. It can also help, I might add, it can also help with maintaining consistent water temperature, especially during those freezing months. During the winter, that you can start have ice formation. So the more that you keep that water circulating, the more likely that water is going to stay at a above freezing point. Okay. So this is just more examples. This picture on the left here is what we call a duckbill valve, I should say. Basically, water's coming up and out these ports. It's going to be this kind of just a rubberized mechanism here. So it's just a little bit with a little bit of pressure coming up, those will actually open up and basically diffuse that water out into the elevated storage tank. Okay. And then on the right here, that's that lower point. So that outlet is going here. Okay. So water's coming up, spraying into the tank, hopefully mixing around and then flowing to the bottom and getting, that circulation going. So this is just kind of showing, what you'd see out of maybe a typical tank. You have, an inlet and an outlet on the same pipe here. So it's going up and it's just going to go right back down. So you're really not getting maybe very good mixing. Maybe it's only a certain portion, especially if you're getting some, short circuiting and things like that, depending on the design of the tank. Okay. Here we have an actual deflection plate. So you're having the water come up and then it's, coming off the sides of that deflection plate. And so now you're getting maybe some more adequate mixing here prior to the water coming back into that outlet portion of that. Okay. So operational issues, mud and sediment. So as water sits there, especially if your system that's known for having, sediment in your wells or high iron or manganese, those things can settle out or oxidize as it sits there, and then you're going to have some accumulation. Now you can see this little mud valve here, but it might not always get that. So having that, mixers or diffusers or things like that, you're having good mixing, and good turnover of your water in general, you might not have that, settling out the same kind of way. So maybe maintaining that, keeping that in solution might be better, at least in terms of longevity of your water tank and making sure you're not having, eventually at some point, maybe pulling that mud or sediment back into the system if it gets high enough. Okay. This is just the lower picture of a mud valve here. So it's, again, just a hole. You have this mud valve here. As you crank it, it opens up that mud valve. It's going to then flow into your usually it's your overflow, pipe that's going out, but it can also be its own separate piping. But again, it just kind of relieves, whatever we have here. Now, as this picture kind of shows, it might not get all of that. So you're going to probably have to do some maintenance at some point in time whenever you take that service or that elevated storage tank out of service. Okay. Here is just an overflow. Now, the biggest thing I want to point about these, because we're going to talk about these over the next couple of slides, is although, yes, that's good. It has a nice concrete pad here, so it can overflow. It'll be great during the summer. You have a screen, although the screen maybe looks a little large. We'd, ideally wouldn't want that 24 mesh screen. But the biggest concern here, especially if you're kind of in northern Michigan where you're going to have cold weather, that's going to basically, that having an open portion here, not a closed flap all the way around, that might create a chimney effect. So as cold air, whips through, it's going to go up, and it's going to come across, the top of that tank and really cool down the top of that water. And basically that's going to be promoting that ice formation at the top. So you might have an ice cake at the top that can cause damage to your tank in lots of different ways. It can cause, vacuum issues, pressure issues, things like that. And just, ice formation in general, maybe it's too much and it fills the whole tank. Now you're not having any storage, things like that. Okay. So we would ideally like a full metal flap. You can't see it super well here, but you're going to have to take my word for it. This is a full metal flap here, so you're not having that same chimney effect, which is good. But the concern here is if you have any overflow during the winter, now you don't have any gap for that to release. So maybe putting a welded bead on here is recommended, or putting a little bit of relief here, so that any trickling of water might be able to leak out. Okay, rather than sealing that flap shut. Now it's basically not worthwhile. Okay, now it's building ice back up into that tube, into that overflow route, and you can have some issues that way as well. So I'm not sure if it's the same tank, but it might be. Probably ideally, they actually put a hole in here at the bottom. So if there's any of that trickling portion of that, it can drip out, so it won't freeze over that cap. Now again, that screen looks a little large to me. It might even have a hole here. Ideally, we want that 24 mesh wire. Okay. And this is an example of that, making sure that you're having those, keeping the insects, keeping the debris, things like that out of your storage tank, making sure it's as sanitary as possible. Okay. So venting is important. It's very important. We talked about this a little bit earlier. Basically, the main goal is to allow airflow in, airflow out. It's important, and then making sure that it's maintaining an ice-free condition as best as possible. Okay. So essentially, why do we need to have airflow? Well, it's important. Obviously, you can have large pressure swings as your tank fills up or goes down. You can have buckling. You can have high pressure issues, with things blowing off or something like that. You can have collapsing, like this picture I will show in a moment. This is actually a tank. I'm not sure the exact reason for this, if it got covered, if it got frozen, whatever the exact situation was, but it actually caused this to buckle because there was so much of a pressure drop there, creating that vacuum and crushing that can. Okay. All right. So this is just kind of a plan view of what a vacuum relief would look like. Those venting systems, so allowing air to come in a couple different ways, allowing air to come out in a couple different ways. in case that there's, no freezing events. So as water level drops, you're going to have airflow in, like I just showed. So airflow in allows, that it won't have that same vacuuming effect. If water rises, I should say, then you have airflow out. Okay. And then what happens if this is frozen here? So now you're no longer getting that airflow here, and you have water dropping. You have a vacuum, occurring there. So we actually have a built-in site, or there should have a built-in second portion of that. Okay, so it's allowing airflow in here. All right. So that's your lower pallet portion. Kind of that backup portion in case something freezes over, or there's debris in it, if birds were nesting or something like that. Okay. Same thing here, frozen there, water level rises, pressure goes up, you might have a rupture event. You're pushing that freezing out of the way, hopefully, and then you're going to have airflow out. All right. This is just an example, and this is the bottom pallet here, right there. All right, so you also have hatches on all of your storage tanks. The biggest thing that this slide specifically is talking about is that this should have a gasket here. Again, trying to maintain sanitary conditions while also making it, workable piece of equipment, right? So that is just would be just steel on steel. That is not ideal. Things can get in there. You can have whatever bugs getting in there and having bacteriological issues that you won't know until you get up there and realize, oh, there's a hole here and there's bugs, okay, or something, debris, whatever the circumstances is. So this is fixing that. Okay, so they put this gasket in, so it kind of seals that off, so you're not going to have those same issues. But here, another issue that you might run into, now the valve doesn't want, or now the hatch doesn't want to close properly, so you can't put that lock or that whatever bolt in place to keep that closed. So you'll have to probably get a little creative, whether that's drilling a new hole or maybe extending this piece and welding a new piece on, to make it work. Okay, so obviously there's always additional problems that come with fixing something that's not proper. Okay, so overflows. Obviously if your water fills up, you need some form of overflow. So here's an example of a weir box. As that water level drives up, it gets to this point, and now it's going to start spilling into this weir box and flowing actually out of the elevated storage tank, in a safe kind of manner. And hopefully there's a concrete pad down there, so you're not having an issue with erosion and things like that. Here's another example of a ground storage tank weir box here. Now this is a ground storage tank, so it's probably not too much of a concern. But if this was an elevated storage tank, this kind of design might not be ideal. If you had some ice caking in there, you have ice formation, it could come up and basically block this outing. So you're still having the same issue, and there's really no overflow because now ice is just sitting in this way. All right. Luckily, it's ground storage tank, so it should stay relatively warm enough where that weir box won't become an issue. Okay, so this is another example of a situation. So weir box up here. Here's your flow. Here's your inlet over here as well. Here's your hatch that they came up through. So this could be a situation that winter goes along, and you have water rising up for whatever reason. Maybe somebody didn't pay attention or the telemetry failed or something. The pumps are still running. And now you have ice caking at the top, and now you're not getting that overflow. Okay, so that's an example where we're making sure your design is proper, making sure your design will adequately address whatever situations you might run into. This is another example of an overflow, but this is probably a more ideal situation. So you have this 36-inch diameter overflow here, notice that it's, completely rounded. So you can have water pouring in from any side. So if you have a little bit of ice chunk coming up to this point, it's not going to prevent it from, still getting water from this side. Okay. It also, as water, if water were to rapidly increase, continue going up, so it's not just spilling over the edge, you would actually get more water flowing out. So it's even better of a situation. You're not having that limited portion there like you would with a weir box. Okay. So that rounded would be more ideal, that circular weir. Okay. This is also this is becoming a common practice with some very large dams on the west side of the U.S. That have circular spillways and things like that allow a lot of water to be discharged very quickly. Here's another example, but this is just a very large one, very large overflow. If it were to ever get very high, it would quickly dispel that water and flush it out the overflow. Okay, so interior tank coating, making sure that your tank is being maintained properly, making sure that it's going to stay in good condition for a long time. So what comes with that, you're having some sort of coating, epoxy coating that usually is sprayed on. So it's recommended that you get your routine inspections in place. So, one little, caveat or note, I guess, that you should take home is, that first bullet point here. So inspect for the first year. Make sure that you get that inspected. If you get it coated by whoever, make sure that you get inspected before that first year, that 365 days runs out, because obviously there's going to be some warranty portion with that. Okay. And then after that, your routine should be every 5 years. At least that's the recommendation from both the Eagle side as well as typically the manufacturer side as well. Interior repainting. So coating life is typically 10 to 15 years, we say, but obviously that's all dependent on how your tank operates, how your system operates, things like that. Maybe you're having ice formations, maybe it's scraping that up a little bit more or something like that. Okay. And then making sure that if you do get that coating, depending on what's going on, you should probably go through a permitting process, or at least talk to your district engineer of Eagle, make sure that is NSF approved to your 61 standard there. You got UL and NSF there. Make sure that this is safe product to be using for your drinking water program. And then, so just in addition to this, after your tank painting, make sure that you're, dump the disinfected water, and then make sure you're sampling for VOCs. Obviously, chlorination may produce high DBPs, and then, making sure that the actual testing of that paint is cured properly and it's not leaching into your drinking water system, causing more potential for harm. And I believe that's it. So any questions?